All right. So thank you everybody for coming. Like y'all are awesome. Um, I don't know. Like I2 has a very special group of people because we're willing to go out here on a Friday evening to listen about AI instead of studying or partying. So thank you guys. And with that, let's get started. So what is natural language processing? It's basically the ability for computers to understand uh, and use and process human language. Some examples of that can include like chatbots, like we've seen, um, text generation, translation is a common but older example of those. Uh, so I remember a couple years ago, before GPT models were ablaze, the best kind of hidden translation model used deep learning, and that was awesome. It really helped me when I was studying abroad. It's also great for sentiment analysis. So given a piece of text, is this text offensive or not? That can be useful for content moderation, but it has its own drawbacks and downsides. So given biased data, your model might find something offensive if it isn't, or it might do the opposite. So it's really important to have equitable data and to take care when collecting that. They're also great at summarization. So if you think of how an entire Wikipedia article, just the first paragraph or so is meant to be a summary of the rest of the article. That's how a lot of the original models or earlier models in the last couple of years were trained. Any questions? All right. So how do we go from words, writing on the screen, to something that a computer can understand? We could give everything a number. Say, A is 1, B is 2, C is 3. That doesn't really work too well because B is not twice A, and C is not necessarily A plus B. So we need another way to represent that. The way we do that is first by using tokenization. We need to break these long strings of text, say a paragraph or a sentence, into smaller chunks. And we do that in a couple ways. We can go by word, that's a common example, or by individual character. And so you would break this text up into the separate pieces. There's also another way that is commonly used in the most prominent and most powerful models right now are using subwords. And I could explain that later if anybody wants to. So the way we go about that is if we're using words as our tokens, we're breaking a long sentence or paragraph up into words. We give each word a vector representation, just like we would numbers or in the past. So have we gone over one-hot encodings, kind of how that works before? Okay, okay, maybe. Basically what we do is we need to we create vectors, as you can see, where there's all zeros except 1, 1 in a singular position. And that allows when we feed those into a feed forward layer, that allows it to select only a certain amount of weights for it. So each vector, or each word by one-hot encoding, now is able to be fed into your linear layers or your model, and those get represented as a vector now. Does that make sense so far? I want to hear questions. Let me have it. So when we're running these one-hot encodings through a linear layer or feed forward layer, the output is a vector. And these vectors actually have some semantic meaning. These outputs are called embeddings. So you can use these embeddings. These are a long vector that represents these words or tokens. And that those are the contextual meaning of that word. And I can give a little bit of an example here. So they carry this representation of the word. It's no longer just one hot encoding, but it's a full-length vector, and we can do operations on these. So if you have similar vectors, those words will actually be similar. So if you have a vector for car and truck, those vectors will actually be pretty similar in this vector space, in these embeddings. So a common example is if you take the vector for king and you subtract man, if you subtract the man vector and you add the woman vector, you're going to get something that's very, very close to the queen vector. Does that make sense? Yeah. Yeah, exactly. Okay, perfect. It's a long, it's a list of numbers, basically. So you go from your one-hot encoding, which is a list of numbers, all zeros except for a 1 in a certain position. And then your embedding is a list of numbers, but that has often more, or those are not going to be all zeros. It's going to be a bunch of real numbers. Yeah.
Where does the embedding come from?
So these embeddings can be trained, and you can do these in a couple ways. I don't know if I have a slide on there. Okay. But one of the common ways that these embeddings are found is with the idea that words next to each other in a sentence are probably have a similar meaning. These you can run and train these embeddings to be similar to words that are near them in a sentence. So if you're given a huge, huge, huge amount of text, you can train these embeddings by making them similar to the words that are near them. So you go from the one-hot encodings, these where there's only one. So you go from natural text, and then you tokenize it. You split it into little chunks. You give each chunk a one-hot encoding, and then when you multiply that chunk, that one-hot encoding, by a linear layer, it's kind of like only activating one of the input neurons. And so that weight gets distributed everywhere. And that weight distribution is basically, that's going to be the embedding itself. Now, when we're multiplying something that only activates one of the neurons, that's actually really, really inefficient. So we'll often use and this is implemented under the hood in PyTorch or other libraries, but we'll use a dictionary lookup, and it will allow it'll make it quicker. You just kind of index into whatever into the embedding table, but it will still pass the gradients through. Okay, so we're going to focus mostly on text generation for this, and I'm going to try and keep all this pretty brief. I'm happy to explain more stuff or go over things later, but I don't want to keep you too long on this Friday. Text generation can be formatted as a classification problem. If you have a certain amount of text, what's the next word? What's that going to be? That's kind of what autocomplete does on your iPhone. If you have a string of words, right? These are tokens. You can try and classify what is the next word. What's that going to be? And that's exactly what your iPhone does. Now, if we take that next word prediction, so if what's the next most likely word after a sentence, we can append that word. And we can keep doing this process to continuously generate text. So I'll give a quick example. If your input text is the quick brown, you feed that into your model, and your model outputs what are the probabilities of the next word. What is that going to be? And if the output, the next most likely word, is fox, you append that word to your original input. So now you're on step 2. You've got the quick brown fox. You can feed that in again and get the next word that's predicted. Append that word, jumps, and you get the quick brown fox jumps. And you can continuously do this process to generate arbitrary length sequences. Any questions? So that type of model is called auto-regressive because it feeds on its previous outputs. And this is how ChatGPT and other generative language models generally work. So we've got kind of our problem defined. We have a input, which is text, but realistically tokens and embeddings, and we need to classify. What's the next word going to be? We can do that using a feed-forward neural network. That's kind of our simplest, most basic building block that we have. But there's a couple challenges with that. Feed-forward networks, they always need a constant dimension as their input. So if you have an image, the images can't vary in size. You can't have a 28 by 28 image and then feed in a 100 by 100 image. And the same thing goes with, the same thing applies when you're modeling words. So you always need the same amount of words or tokens in your input to the model or a feed-forward neural network so that the model can work. Does that make, okay, yeah. And we call that the context length. What's up?
Good question. So like when you start and say the context length is like quite long, I'm just curious, does it vary model to model? Like what they do, is it just a bunch of start tokens to do something else at the very beginning? Or?
Yeah, that's a good point, and I'll get to that in just one sec. So you need a constant amount of inputs. And that raises a couple questions. What do you do when your context length is shorter than how long your string is, how many tokens you have? That's the second example. If your context length is 4 and your input is an apple a day keeps a doctor, well, it can't take in the first couple words. It doesn't have, it can't look that far back enough. Yet, also, if you have a very short sequence of tokens, say only 2 and your context length is 4, you need some way to, put in fake data almost, or put in filler data. And we call these often padding or special tokens. And those are tokens that the model basically learns are unimportant, but you have to add them as filler. And so different models are going to use things differently. There's no general way that it's always done, but you'll often have a padding token or a start token if your sequence is shorter than the context length. But those are some of the big issues with feed-forward neural networks in this using this task. They can only take in a fixed context length. If, say, you want to use your neural network and you start on some very short sequences, but you also want to train it on to be able to take in long sequences, you're going to waste a lot of compute and data. Additionally, feed-forward neural networks struggle to capture some of these, some of the dependencies between the tokens. This is kind of similar to how in images you use convolutional layers, because that allows the network to kind of look at things that are close to it. And while we won't use exactly convolutional layers with language, we're going to do something kind of similar to that in the future. Additionally, feed-forward neural networks don't have an internal representation we can use for something later. It doesn't get better, really. So here's a second thing that you can use, is recurrent neural networks. In these RNNs, they keep an internal hidden state, and that represents everything that they've seen so far. So that's kind of like what you're thinking as you read through a sentence, what you remember. They read each token one by one, processing them in sequence, and they update its internal state after each token. So that's like reading a sentence, and after you read each word, you figure out, okay, what do I remember so far? And after each word, they also generate predictions for the next word using the hidden state that they have. So at each step, they basically they read the word, update what you remember, and use what you remember to predict what's the next word going to be. This is what they look like. You feed in an initial hidden state because it needs to start with something. And each time you feed in, at each step, you feed in a new token. This token is processed. It updates a hidden state. And then an output token for what's the next most likely word is generated. And this process repeats over and over again for each token in a sentence or in some text. These updates in generation, they can be done using a simple feed forward layer or something else. Any questions so far? Yeah, so it's the kind of, it's what you remember after, like, before you even start reading something. And like, we don't have that. We obviously don't need that, but neural networks, they need to start with something. So you just, often that's initialized to all zeros. It's like, all right, it knows nothing so far. We're going to update from there. I'm not exactly sure what you mean. Mhm. Right. If that would probably be problematic. It would kind of, it would learn like, hey, this is, I know nothing so far, and then you'd start it out with its thinking like the past is some gobbled mess. So that would be a problem. Generally want to you generally don't want to treat the network differently between training and inference. If you train it with zeros, you'll often want to initialize it with zeros. And what are the advantages for RNNs? Well, they're really efficient. These feed-forward layers inside them that update the state and generate the next token, these can be reused across each step. And that might not sound like a huge difference, but that allows the model to be very, very, very efficient compared to feed-forward layers. Sorry, an older feed-forward neural network with a fixed context length. RNNs also can take in any arbitrary length of text because it just does the same process over and over again for each token. And then they also have an internal representation. And this is great because after, say, you feed it through a sentence, it has its hidden state, what it remembers so far. If you have another task, say you're trying to classify if something is offensive or not, you have that memory, that representation of what the text is so far. So you could just run some sort of classifier on that memory at the end of a sentence. There are some disadvantages, though. They tend to forget over long sequences of text. So it's kind of like how we might read or something. If we end up reading a really, really long sequence, it will continuously rewrite and re-update what it remembers at each step. And so you're going to lose kind of that memory of the first things that you've seen. It also doesn't have a great mechanism for the relationships between tokens. It can't say, hey, let's look at the first word and the third word and see how they connect. It can only look, the third word can only look at what it remembers so far, which is one vector. It also has gradient issues. These gradients, when you're training this network, they can grow really, really big, or they can vanish to almost zero. And that makes training RNNs really unstable sometimes. Questions? I don't believe you guys. All right. And so transformers come here to save the day. All right. What transformers use is they use self-attention to allow these inter-token relationships. What that basically means is the tokens can look at each other, and they can understand basically how they relate to each other. They're state-of-the-art in many fields. Right now, you've seen, everybody's seen chatbots and whatnot, but in computer vision, these are also used in some of the best models. I'm going to briefly go over self-attention, and I'm happy to talk about this afterwards or give a longer lecture, but it's kind of in-depth sometimes. So basically what it allows tokens to do is score the relationship between other tokens. So if you have a sentence, the quick brown fox, the and quick can look at each other and see, hey, how are these words correlated? That's really important because in sentences where things might not be clear, say, I ran to the store, it was hot, you don't know what it is independently. It needs to look at store to figure out, hey, what does it mean? So it allows, self-attention allows these tokens to look at each other, see, hey, how do we relate? Is our relationship important? And then draw information from these other tokens. I'm happy to, after this, I'm happy to explain how that's going. What's up?
So if you have like the word cat looking at the word bat.
Yep.
And the word bat looking at the word cat. Bat has a score for cat has a score for bat. Is it the same score?
Not necessarily. Or no. Each of these words, they generate a query, a value, and a, good God, query, value, and key vector. And basically the query vector means, hey, what am I looking for? In terms of it's looking for probably a noun. The key vector is like, hey, what am I? That would be like, hey, I'm a noun. And then the value vector is, what do I represent? So it roughly goes, if I'm a token, I have my key, I'm looking for, hey, does my key match with other people's, or sorry, goddamn. I have a query vector. I'm comparing my query vector to everybody else's key vectors, saying, hey, are you what I'm looking for? And if so, I take your value vector, what you represent. So cat and bat, they're going to have different query, key, and value vectors. So they compare different things. No. What are they really good at? They capture relationships between tokens super well via self-attention. They're also able to be trained in increasingly parallel ways. So RNNs, you have to go step by step by step to even update the hidden state. Transformers, they take everything in at once. In the performance skills with parameters, so you can just kind of dump more and more parameters and more data and more compute, and you often get a model that is a lot better. Some of the disadvantages are they are very compute hungry. They rely on a lot of data, and this can cost a huge amount of money. So training large language models from scratch is millions and millions of dollars, even for like smaller models than say OpenAI's. And they're not very explainable, especially with the amount of parameters that you have. That's really, you can't really look at one or two or a lot of even more parameters if it has a billion parameters and understand what that represents. So one of the things, because these models are super challenging and expensive to train from scratch, is people will fine-tune them. So you'll take a pre-trained LLM, so one of these models that has been trained on a lot of text, so it kind of understands language a bit. It's not perfect at a specific task, but it understands English for the most part. And you'll do additional training on that model. So an example of that is you might take a older model, say GPT-2 or Llama, which is a very general model. It kind of understands English. And then you'll get a specific data set for the task you wish to use your model on later. So say healthcare. You might get healthcare data or medical data, and you'll further train your model on the healthcare data or that healthcare information. That allows the model to kind of leverage, hey, I understand English already. I've done that like hard part, which costs a lot of money. now I can get really good at this specific task. And then alignment. These models are as biased as the data is passed into them. If you give it really biased data, you're going to have a really biased model. They can hallucinate facts, and they're often wrong. They're generating the next token probability. That's not how we do math or anything. We don't think like, hey, we don't look at addition, or actually addition maybe, but multiplication and order it in number after number and think, okay, what's the next number to come after it? No, we go through an algorithm and we think about that more in depth. And these models only generate the next most likely token, but that's often not how we want to interact with them in practice. If you, we often want them to give responses to our questions, yet it's just trying to generate future tokens. So if you give it a question, an unfine-tuned model, unlike chatbots that we see now, they're just going to try to continue that question. It might ask further questions like that. If you gave it an exam question, it might try and write more exam questions. That's not what you want. So these models will rely on additional fine-tuning, and that's often used. That's often done by reinforcement learning to get a lot better at interacting in the way that we want them to. That's it. Thank you, guys. Questions?
Like when you're doing RNNs and you're first starting off, like you just have to look through like thousands of crappy responses before you get one good one, give you a little model treat, or what?
So RLHF is reinforcement learning from human feedback. The human feedback is kind of a misnomer. It's generally another model giving it feedback. Basically what that process is you have your original LLM output some response. You take another model or a human or something else to score that response. Was that a good response, a bad response? You give that a numeric score. Say, 1 if it's good, -1 if it's bad. Then you pass that into the reinforcement learning algorithm, which is PPO. It's a bit more complicated than what we've gone over in the past, but not that much more. And you'll pass that in, and it will learn, hey, this is a reward. It was a low reward. Let's not do that as much. So when you're starting out, yeah, there are going to be a lot of, humans don't end up generally annotating these things. Reinforcement learning from human feedback is generally not the case. It generally is not from human feedback. It will use an additional model to score, hey, was this response toxic or no, or something else. Yeah. Mm-hmm. Yeah. So not really. So plugins for a chatbot might be allowing it to search the internet. The way that those are implemented is you'll give these, say, chatbots are going to have information fed into them at the start of the conversation saying, hey, you can use, if you say the word internet search, you can search the internet just like you make an API call. So it's allowing the model to generate responses. And if it's a certain string of text, say it's like search internet parentheses and then your search query, that model will be able to use some API. It's not another additional network, typically. Does that answer your question? Yeah, yeah. Well, so yeah, so that one's a little bit different. So these document readers or image if you have the premium version of ChatGPT, you can pass in images. Those images are processed using another neural network typically. So RNNs, what you mentioned before, like how do you initialize it? One of the ways that RNNs for image to text that works is the hidden state will not be all zeros, but the hidden state will be the result of a convolutional neural network or an image model. So in that case, yes, you might have another model kind of classifying or processing these images. Okay, yeah. So you can leave if you want, I guess. I'm also happy to talk about, I have another presentation on transformers, which I could talk about after.